All right, good morning, everybody. So before we get started on the stuff we want to do today, I want to go over some of the problems that you went with my graduate student at the end of the last lecture while I was gone. So let's look at the first one. This is going to be a nucleophilic substitution reaction, right? So we have to identify the electrophile and we have to identify the nucleophile. Another name for an electrophile is a Lewis acid. All electrophiles are Lewis acids, okay? And it turns out that alkyl iodides or alkyl halides in general are Lewis acidic. And how is that possible? How is it possible that this iodo compound is a Lewis acid?
Because you can make a conjugate base out of it.
Well, I will have a conjugate base that comes out, yeah, but what is a Lewis acid? What's the definition? What kind of electron acceptor? Just electron acceptor? Electron pair acceptor, that's right. And if we look at the carbon-halogen bond here, right, is it polar, non-polar? And why is it polar? Okay, iodine's in the halogen family, right? It's fairly large, it's polarizable. We know that that bond between the carbon and the iodide is fairly long. Remember that slide, right? And so if we think about that, where are the electrons in that bond spending more of their time? Around the iodine or around the carbon? Around the iodine, right? And so that puts a partial negative charge on the iodide part, right? So what happens to the carbon? Partially positive. And so we have a dipole in that direction. That carbon being partially positive means it can accept electrons. Where can it get electrons from? From the nucleophile, which is the nitrogen, right? So if I think about this, I've got sodium plus and I've got N3 minus. Right? So I'm going to show the actual Lewis structure. Nitrogen can be a nucleophile because it has a pair of electrons, right? All nucleophiles are Lewis bases, but not all Lewis bases are nucleophiles, okay? That's a rule that you need to remember, okay? But it turns out that azide, N3 minus, is actually a very good nucleophile. So how does it work? How do I draw the arrows? Right here? Okay. The carbon, it's going to go from negative to positive, right? And so I've got a partial positive there. Now what happens? That's right. Plus I have sodium as a spectator ion and iodide as the leaving group, right? Iodide's a good leaving group. I know that because it's in the halogen family and it's at the bottom, right? Yeah, that's right. It's a weak conjugate base. Weak conjugate bases make good leaving groups. And so that's how we show that reaction. This is nothing more than the reaction of H plus and OH minus to make water, really, right? Negative reacting at positive, okay? We're just pushing those arrows. It's Lewis acid and Lewis base. If you can identify the Lewis acids and Lewis bases in most organic compounds, you know where the chemistry is going to occur. 95, 96% of all organic chemistry really is nothing more than the reaction of Lewis acids and Lewis bases. That's why Lewis theory is so much more important than those other two. Bronsted and Arrhenius are, from an organic chemist point of view, are essentially useless. But Lewis theory explains a whole lot. Okay? How about this second one? Pretty much the same thing, right? We have a situation where the nucleophile is going to attack the carbon. The leaving group is going to leave. at least at this stage, we end up with this molecule. I know that I have to have a positively charged nitrogen, right? Because of how do I figure that out? Okay, so I went from a neutral nucleophile. Yeah, that's right. So it's got to be positive. Here I went from a negatively charged, so it has to be neutral, right? But I could also calculate it just from formal charge, right? So that works pretty well. So let's look at this. I can take an alkyl halide and I convert it into an azide, which means I just made a carbon-nitrogen bond, and that turns out to be pretty important. But I can also react alkyl halides with amines, and I can make carbon-nitrogen bonds, right? You should be starting to see that we're going to be able to do an awful lot with an alkyl halide. Alkyl halides are one of the more useful functional groups in organic chemistry. Now notice here, I wrote the salt, the sodium azide, over the arrow. Here I wrote plus. I just want you to see that there are multiple ways in which you can write organic reactions. Both are completely accurate. They're both the same thing. That's right. And here I've done this in several steps. How do you handle a problem like this? One step at a time. And I guarantee you, just about every one of you will look at this problem and try to figure out what the final product is without doing it step by step. I don't know why. Every year I say the same thing, don't do it, and everybody does it. So I know you're going to do it. But let me tell you again, don't. Take it one step at a time. Don't worry about this other stuff. The first thing you worry about is this. Okay? So let's worry about this. What's the electrophile and what's the nucleophile? Okay, so here we have the electrophile. Where's the nucleophile? Well, it's not the sodium part. It's the sulfur, right? So really I have SH minus and sodium plus. Just for your information, S minus, sulfur minus, is what we call a supernucleophile. Okay? They react very well. Okay? So what do we have? How are we going to push the electrons? Where am I going to start? Okay. And? That's right. So the product from this first reaction is this. So what did I just do? I converted an alkyl iodide into what's the functional group here? A thiol or a mercaptan, right? So notice I can take alkyl iodides and make, or alkyl halides and make azides. I can take alkyl halides and I can make ammonium salts. And I can take alkyl halides and I can make thiols. A lot of different things that we can do. Okay? So that's what we get for this first question mark, and that's what we would write there. Now, what about this business? What does the 1 and the 2 mean over that one arrow? All right. This keeps me from just having to write multiple arrows. If I did not have 1 and 2 here, you would assume that everything is added at the same time. Very important that 1 and 2 be here in this particular context. So 1 would be simply taking this and reacting it with sodium hydride. What's going to happen? Why? It will make hydrogen gas, but why? Why doesn't the hydride just come in and react and kick out the SH minus? The stronger one or whatever.
I have it in my head. Go ahead.
It is a base, but bases can also be nucleophiles, but not always. This is one of those cases. Sodium hydride is not a good nucleophile, but it is a good base. Hydrogen has a pK of around 35, somewhere in that range. So this is a pretty strong base. So you're right, we're going to have a reaction where the hydrogen, or the hydride reacts with the hydrogen on the thiol. We end up generating hydrogen gas, which bubbles out a solution. And we get another S minus. Now we throw that into iodoethane. What happens then? What happens? Switch the two what? So the iodine's going to go where the S is? The whole thing? The ethyl part? How? Tell me how to push the electrons.
So from the bond to the I to the, wait, no, to the I from that carbon.
Here?
Yeah.
Okay.
And then from the S to the carbon.
Yep. That's what we've got going on. This will come to you with more practice. You will not get it all watching me do problems. I promise. You watching me do problems, you'll leave and you'll say, that makes sense, and then you'll go and you'll try to do it and you'll go, right? You have to practice.
So the sulfur stays because it's not a good leaving group.
It's not a good leaving group.
So it stays and just reacts with other stuff. Okay.
Well, we know that halogens make good leaving groups, and we know that water makes a good leaving group at the moment. So that's how we know that at the moment. We'll learn more about good leaving groups and other things as we move along. Okay? So today we're going to start talking about the mechanism of substitution reactions. Okay? And what we've been drawing here is mechanistic. We just haven't really talked about it in terms of mechanism. Okay? We're going to learn how to determine what type of mechanism a reaction must be in a substitution. And there are a couple of different types of substitution reactions that we'll be discussing. Okay? So we know that in these nucleophilic substitution reactions, we have to have a nucleophile. What separates a base from a nucleophile? Both have lone pairs, but a base attacks a proton, not carbon, right? So if we have a good nucleophile, it's going to have a lone pair of electrons just like a base does, but the nucleophile will actually attack the carbon of the electrophile. A base will not attack here. It will attack a hydrogen somewhere. And alkyl halides can actually undergo reactions with bases to do elimination chemistry. Okay? But that's the big difference. Nucleophiles attack carbon, bases attack hydrogen. How do we know which is which? We'll learn with time. Okay? We'll see several examples, and you'll be able to figure it out, I promise. Okay? There are some nucleophiles, however, that can function as both nucleophiles and bases, and that gets a little more complicated. Okay? But the rule that I want you to know is what? All nucleophiles are very good. Okay? So, for example, right, if we have a base, we can do what's known as an elimination reaction, which we'll talk about at the end of the chapter, beginning in the next chapter, and we can get alkenes. That is the reverse of an addition reaction. Okay? But what we're talking about in this chapter is the nucleophile actually attacking the carbon atom. What makes a good nucleophile? What did you learn last time? What were some of the things that were good nucleophiles in that list? They all have to have a lone pair of electrons, but that doesn't necessarily make them a good nucleophile in and of itself, right? Okay, they're going to have weak conjugate bases. What else? Well, you're talking about leaving group there. Yeah, let's not get that confused. They can be strong bases, but I can also have strong bases that aren't good nucleophiles. Sodium hydride is a very strong base, pK of 35. Not a good nucleophile. Most good nucleophiles, if we look at them, were what? Negatively charged. You can have neutral nucleophiles and you can have negatively charged nucleophiles. The negatively charged nucleophiles are almost always the better nucleophile. They've got an excess of electrons, if you will, because they're negatively charged. They make really good nucleophiles. Okay? Now, it turns out that, as you have rightly said earlier, that nucleophilicity and basicity are related, but they are different, okay? When we are talking about how basic something is, we're talking about a thermodynamic property. When you talk about acids and bases, you talk about an equilibrium constant, right? KEQ equal whatever. In this case, you'd be doing the Ka, right? Which essentially is an equilibrium constant in a way, right? So when we talk about acids and bases, we talk about pKa, right? Just like when we talked about sodium hydride, I told you that the pKa was around 35, right? That's all thermodynamic. When we talk about nucleophiles, though, we don't talk about equilibria so much as in terms of how nucleophilic something is. We talk about rate. Good nucleophiles react very, very quickly. Poor nucleophiles react slowly. So if something has a really fast reaction, that's because it's a good nucleophile. If it has a really slow reaction, it's because it's a poor nucleophile. Okay? So that's fundamentally the difference. When we're talking about acids and bases, we're talking about thermodynamics. When we're talking about nucleophilicity, we're talking about rate. That's the big difference. What determines the rate of a reaction? Temperature can affect rate of reaction, so these values have to all be at the same temperature if we're going to compare nucleophiles. pH level? Yeah, it could. Concentration definitely determines rate, so we have to know what concentration our nucleophile is if we're comparing nucleophiles. It wouldn't be fair to say I have 20 molar of this nucleophile and a millimolar of that nucleophile and make a comparison, right? You need to have similar comparisons to make. What else? Solvent makes a difference, so you usually have to think about these all in the same solvent. What else? What determines the rate of any reaction? Catalysts can actually lower the rate of reaction, but I'm talking about uncatalyzed processes. So you're not incorrect, but let's just take an uncatalyzed reaction. What did you learn in Gen Chem? Three letters. Q, no. Rate determining step. What is the rate determining step in a reaction? It is the slowest step, and it's the slowest step because it has the highest energy barrier, right? The tallest mountain that you have to climb is going to determine how fast you get over, right, onto the other side. So all those things are going to come into play as we talk about nucleophilicity. So some common nucleophiles in organic chemistry. Certainly by no means is this an exhaustive list. There are entire books on this kind of stuff. But notice we have a lot of negatively charged nucleophiles. Hydroxide makes a good negatively charged nucleophile. Alkoxides. What's the difference between an alkoxide and hydroxide? Carbon, that's right. So these have similar chemistry or different chemistry? Very similar chemistry. Acetate. This is a salt of a carboxylic acid. Our good friend azide, very good nucleophile. What's that one? Cyanide is also a very good nucleophile. We use it quite a bit in my lab. Alkanides, the halogens, bromide, iodide, chloride. So which one of these do you think is the better nucleophile? Iodide. It turns out that as you go down a family, you end up having better leaving group, and you also have better nucleophiles. Oxygen is a poor nucleophile than sulfur. Sulfur is a poor nucleophile than selenium, so on and so forth. Leaving groups, as you go down, increases, but so does nucleophilicity. Okay. Sulfur, we can have SH minus, very similar to OH minus, and we can have RS minus, very similar to OR minus. Okay. All of these nucleophiles are negatively charged, and all of these are very, very good nucleophiles.
So how does going along the period matter? Like comparing like sulfur to chlorine, or which one would be better? Can you make that?
Sulfur is a better nucleophile than chlorine, than chloride.
So would that be the same thing for selenium and bromine?
Mm-hmm. Chloride is a better leaving group than what? When we're comparing in a family, we have to just think about it in the family. Right? Chloride is a poorer leaving group than bromide, which is a poorer leaving group than iodide.
So would it be the size that matters?
It does.
On the tube, it's like when you're comparing in a period?
No, when you're going in a period, it has the size is actually getting a little smaller, right?
Well, you said that sulfur was better than chlorine. So
As a nucleophile, yes. It's a little larger, less electronegative, right? Doesn't hold on to its electrons as well.
okay, that makes sense.
Okay. We also have neutral nucleophiles. Water. Why is water a nucleophile? Because you have lone pairs on oxygen, right? Alcohols can also be nucleophiles. Ammonia can be a nucleophile. A primary or secondary amine. And then H2S, dihydrogen sulfide, or thiols can also be nucleophiles. If you've ever worked with H2S, which we do quite frequently in my laboratory, you'll know a particular property about it. It really stinks. It'll drive you out of the lab really, really quickly. These things stink bad, so we try to avoid them if we can. But we can have negatively charged nucleophiles, we can have neutral nucleophiles. Now let's think about some mechanisms, some potential mechanisms for this nucleophilic substitution. The overall reaction is really easy to see. We are substituting, right, the nucleophile for the halogen. We're just basically doing a bond swap, if you will. But there are at least a couple of ways in which we can imagine this happening, right? We can imagine that bond making and bond breaking occur at the same time, which is kind of what we've drawn up here. Not kind of, it's exactly what we've drawn up here, right? As I'm making the carbon nucleophile bond, I am breaking the carbon leaving group bond. I am making a bond and I am breaking a bond at the same time. Okay? Does that strike you as odd? What do you know about carbon? How many bonds can it have? 4. So as I'm making a bond, but I still have it bound, right? So is that strange? It's almost like there's 5 bonds around that carbon, right? But since we are starting to make a bond and we are breaking a bond at the same time, you can kind of think of them as half bonds, if you will. Okay? We kind of fudge the numbers a little bit. Think of it like that. Okay? Now, if we think about this, this would be a one-step mechanism. The rate of that reaction is going to depend on 2 concentrations. It's going to depend on the concentration of the electrophile, and it's going to depend on the concentration of the nucleophile. Why? Why would it matter? Why would it matter what the concentration of the nucleophile is, for example? Well, there's the rate equation, but I'm trying to think of it from a conceptual point of view. Why does that rate equation have to be what it is?
Because you didn't have very much nucleophile compared to electrophile, and it wasn't going to do a full reaction. There'd still be some carbon, there'd still be some alkyl halides left if you didn't have enough nucleophile.
Okay, but that doesn't explain it. What about that reaction means that it has to depend on the electrophile concentration and the nucleophile concentration? Pardon? Okay, I have one step, right? So that step has to be the rate determining step, right? What's involved? Both species, right? These species actually have to collide with one another for this to work, right? So if I double the concentration, let's say, of both species, what do I do to the rate? I increase the number of times that they bump into each other, right? If I bring everybody in here, a bunch of students, and I just have them walk around at random, you guys are going to start running into each other quite frequently, right? But if I only bring 2 people in here and I say just walk around at random, how often are you going to bump into each other? Not as often, right? That's like concentration. Right now, you guys are concentrated in this room. And if I told everybody to leave but just 2 people, it would be more dilute, right? So the number of collisions that we would have in a given amount of time would depend on how many people were in this volume. And that's essentially what's going on here. So in this one-step mechanism, the rate is going to be proportional to some rate constant times the electrophile concentration times the nucleophile concentration. This is a second-order reaction overall. It is first order in electrophile, and it is first order in nucleophile. So if I gave Yusuf a reaction, and I said, you're going to use 1 molar electrophile, 1 molar nucleophile, he would find a rate, right? He could calculate the rate. But then if I asked Jessica to double the rate of or double the concentration of the nucleophile from his reaction, what would happen to her rate? It would double. What if I had you double both the electrophile and the nucleophile? It would quadruple, right? It's first order in both, second order overall. Yeah, right? So if we double one species, we double the rate. If we double both species, we quadruple the rate, right? And so we could figure out if this mechanism was true for these reactions by doing what? Let's say I think that this is a second order reaction. How could I prove that?
Run it, double everything, run it again, see if the rate changes.
Could. You'd have to do certain. You did this in Gen Chem, right? You did reaction kinetics, where you took one species, held it constant, doubled the other, right? That's exactly what we would do. And if that rate follows this law, we would say that this happens to be a second order reaction where the bond making and bond breaking are occurring at the same time. Well, you'd put a half and it'd quarter. Yeah. So we could follow that pretty easily. This is known as an SN2 reaction. What does SN2 mean? What's S? Substitution in nucleophilic to bimolecular. Second order, basically, right? So, yes, this is an SN2 reaction. We can also imagine a reaction where the leaving group leaves, I get a carbocation, and then the nucleophile attacks that carbocation, and I get the product. What's strange about that mechanism? Carbon doesn't have all 4 of its bonds. But what did I tell you at the very beginning of the semester? Carbon can have less than 4, at least for a fleeting moment, right? So it is possible that this mechanism could occur, okay? Which one of these steps would you suppose to be the rate determining step? The first one or the second one? Why?
Because the bond's got to break before the nucleophile.
Okay, so we got to break a bond, and that's always takes energy, right? Okay, that's very good. Why else would you say that that one has to be the rate determining step? The fact that carbon doesn't have an octet, right, means that that's going to be high in energy. That's going to be the rate determining step. Why would the second step not be rate determining? I'm forming bonds, right? So we know that that's an energy releasing process. And carbon is gaining its octet back, right? So that should happen really quickly. So we know that the first step happens to be the rate determining step when we think about this theoretically. Notice it's a 2-step mechanism, but what can you tell me about the rate? That's right. Only the rate determining step matters. So the rate of this reaction is only dependent on the concentration of the alkyl halide, because that's the rate determining step, the alkyl halide going to carbocation. Nucleophile never comes into play, okay, in terms of the rate. That's the slowest step. That's what the rate law is going to be dependent on, right? It's a first order rate. How would we prove whether or not these were first order? What would we expect? If one of these was a first order rate like this, what would we see? Of? That's right. So if we doubled the concentration of alkyl halide and we saw that the rate doubled, that in and of itself does not tell us anything. Okay, so if we double the concentration of the nucleophile and we notice that there's no rate change, now we know, right? Because actually doubling the concentration of alkyl halide would double the rate in both cases. But we would also have to run an experiment where we doubled the concentration of nucleophile, and if we notice when we do that we see another doubling, we know it has to be a second order reaction, and in this case it has to be a first order. Do not get this confused. This is a two-step mechanism, but it is an SN1 reaction. The 1 and the 2 in SN does not tell you the number of steps. It tells you the order, right? So this is a substitution nucleophilic unimolecular. Yes, ma'am. We will learn how to distinguish that. Okay? There are reasons why we would predict that this would occur first. Anything that stabilizes a carbocation, for example, favors this reaction. And we'll talk about that a little bit later.
So you were saying, like, I understand the second order reaction because of, like, the rate constant times the nucleophile and the other one.
Mm-hmm.
That's why when you double them. But what if you doubled both of them and, like, only one affected it?
Then you probably have this mechanism.
Okay.
Yeah.
So then it would be a first order reaction.
You can double both, but if I only noticed that the nucleophile had no effect, then it has to be this particular mechanism.
Okay.
Now there's a third possibility. We can have bond breaking and bond making at the same time. We can have bond breaking followed by bond making, but we can have a third example, okay, where bond making occurs before bond breaking, okay? And this one is, at least for organic chemistry, is absurd because we can't exceed the octet on carbon. This would have a pentavalent carbon that would actually exist, and we don't have the orbitals to account for it. This type of mechanism does occur in inorganic chemistry, and you may have seen some of that when you took Gen Chem or when you take your higher level inorganic chemistry class. You will see examples of things like this if you have metals here, okay? Things that have other orbitals. But for carbon, this isn't a possibility. So really, as far as we're concerned right now, we have two possibilities. SN1, which is first order, and tell me the mechanism. How does it work? Bond breaks, so the leaving group leaves. We get a carbocation intermediate, then the nucleophile attacks. And then we have SN2, which will have a simultaneous reaction. That's right. Okay. So if we look at an SN2 reaction, this is what we think the transition state kind of looks like. Notice how they've drawn the bonds to carbon between the nucleophile and the leaving group. What can you tell me about that? They're dashed, meaning that they are partial, half. I'll buy that. All right. What else can you tell me? What's the geometry of the nucleophile and the leaving group? 180. That's right. In organic chemistry is a very violent sport. We say things attack each other, okay? You can definitely tell that would go well with the current presidential debates, right? But the nucleophile comes in and attacks from the back and kicks out the leaving group. Students really love this because you can literally think of it as something coming in and kicking out the leaving group. That's not really what's happening, right? But as the nucleophile approaches from the back, the leaving group leaves on the other face. This all happens at the same time, and since these are partial, we kind of fudge things and say there's really only 4 bonds. There's just 2 partial bonds involved, okay? What else can you tell me about the geometry of that carbon atom? It is no longer tetrahedral. If you look at it, right, just the carbon without the, I mean, it kind of becomes sp2-like in a way, okay? Ignoring the nucleophile and the leaving group, if you want to think of it that way. That's the transition state. That's the highest point of the mountain, okay? The energy of activation is here, okay? Why must the nucleophile approach from the backside? Okay, very good. So if I have, remember, us organic chemists, we're lazy. We don't draw in everything, right? The bromine has lone pairs around it. All nucleophiles have a lone pair, right? Whether they're charged or not. Is that going to come in from this side? Negatives repel each other, right? How can it get as far apart as possible? 180 degrees. That's exactly right. But that is a very simplistic model. And it works. What's the real model? I've got a carbon-bromine bond. Bonds are really orbitals, right? Where electrons reside. So if I have a bonding orbital, I also have a what? An anti-bonding orbital. And that anti-bonding orbital looks like this. So what is the nucleophile really interacting with? The anti-bonding orbital. So the nucleophile comes in. It's not going to approach here because there's all these lone pairs. But it approaches here. And as soon as those electrons get into that anti-bonding orbital, what happens to the bond? It starts to break. So as the nucleophile's electrons start to populate the orbital, the bonding orbital starts to break. You learned all that in all those diagrams you did in Gen Chem, right? If you put electrons in a bonding orbital, that's a good thing. When you start to put electrons in an anti-bonding orbital, bonds start to break. That's what's happening here. Okay? So you've got two ways to think about it. You can think about it on an electrostatic repulsion, which works. But the real reason is orbitals. Okay? And it has to do with the fact that you are actually occupying an anti-bonding molecular orbital to get that reaction to occur. Okay? Now, it turns out that there are other ways we can prove this mechanism. The rate does not tell me how the nucleophile has to approach. It just tells me that the nucleophile and the electrophile are involved in the rate determining step. Right? Does that make sense? But I just told you that it has to come in from the backside and kick out the leaving group, right? From the rate equation, that doesn't tell me that. So how do we prove that? We prove that using stereochemistry. We prove that using the information we just learned in Chapter 5. Okay? So we start off with a chiral substrate. Notice this is an alkyl halide. It's got a bromine, it's got a hydrogen, it's got a deuterium, which is just heavy hydrogen, and it's got some carbon group. What's the stereochemistry at this, assuming that, let's say that that's a methyl group? What would the stereochemistry be with the hydrogen going away from me? Is it RS? It is S. 1, 2, 3, right? Hydrogen's always the lowest priority. So that's S. What about in the product? It is R. Assuming the nucleophile is like a halogen, right? Something heavier than carbon. It would be 1, 2, 3. What happened to my stereochemistry? It inverted. It flipped. Okay? That's how we know that the nucleophile has to approach from the back. So as the nucleophile comes in using these colored spheres, okay, we go through this planar transition state, if you will, and then that inverts. We call this umbrella inversion. Why? Where do I get that term, umbrella inversion? It's kind of like I'm holding an umbrella, right? And I'm walking out in the storm when all the wind, what happens to my umbrella? Assuming I don't have one of the fancy ones with all the louvers. It pops open, right? That's exactly what's happening here. It pops open and it gives you the other umbrella, the one that catches the rain. Okay? Not deflects the rain. Yeah?
So, between the leaving group and nucleophile, so the nucleophile needs to be less electronegative than the leaving group, or for it to be a leaving group?
Typically it is, but not always.
But it doesn't have to be?
Doesn't have to be.
Okay.
Now, whether or not the position of the equilibrium lies, we could start talking about those things. But for right now, let's assume everything goes to completion. Okay? So, how would we physically do this experiment in the laboratory? Gabriella wants to prove that the reaction she's doing is SN2. She's got the rate data, which suggests that it's an SN2 reaction. But she wants to prove it even further, and she wants to do something where she shows the inversion of stereochemistry. What machine? A polarimeter. That's exactly right. We start off, we get a polarimetry value for the starting material, and let's say it rotates in the positive direction. And so we know that that has to be the S configuration. then we would take the product and we would do the same thing and determine that it has a different rotation that matches up with the R stereochemistry. That's how she would prove this. Okay. So if we look at some examples, here we have, what is that? 1, 2, 3, 4, 2-iodobutane. What is that, R or S? I'm turning to the left, right? So it's S. We react this with SH minus, which is a supernucleophile. It attacks from the back. The leaving group leaves. And now what's my stereochemistry? It is R. 1, 2, 3. So we go clockwise. 1, 2, 3, to the right. We've inverted the stereochemistry. Likewise down here, we invert the stereochemistry. Okay? Let's see, yes, that is S, and it becomes R. Notice how they cheated a little bit and just drew these swapped, right? It's not really cheating, but it makes it a little more difficult for you to determine because the hydrogen's pointing towards you. It looks like it's going 1, 2, 3, right? But you got to flip it, which means it's actually going the other way, right? So we're looking at Big Ben from the wrong direction. Okay? Now this has a lot of practical uses, this SN2 reaction. It turns out that they use this all the time in the pharmaceutical industry. So for example, if you take this amine and we react it with this dihalide, it just happens that we've got 2 alkyl halides connected together. So we react 2 moles of this with a single mole of that, we get this molecule, ethambutol. Anybody know what that is? It's used in inhalers. So if you're an asthmatic, you may have taken ethambutol before, okay? It is made simply by an SN2 reaction. Notice, however, that the starting material is known as an amino alcohol for obvious reason. It's got an amine and an alcohol. It has 2 nucleophiles in there. Which one's reacting? Nitrogen. Nitrogen is a better nucleophile than oxygen. Why? Okay, and why? What does that mean?
It's less likely to hold electrons.
Okay, that's right.
Will be avoiding.
The lone pairs on this neutral nitrogen are more nucleophilic than the lone pairs on this neutral oxygen because of electronegativity. So as we move from left to right in the periodic table on a period, nucleophilicity decreases. That's exactly right. So nitrogen is a better nucleophile than oxygen. We just did the experiment to prove it, right? We made ethambutol. We can also use methylamine, make this carbon-nitrogen bond, and in one step you get Prozac, which is a very important antidepressive, right? But it's made using an SN2 reaction. The point I want to make here is that these reactions that you all are learning, you all will use when you get to medical school. When you're studying the human anatomy and how the biochemistry of all this works, you will be talking about organic chemistry. Okay? If you ever want to go to medical school. Huh? Do I think you will what? I hope so. I have faith in you. I believe in you. Now here's an example. Here's an example. In the human body, you do not have alkyl halides that are reactive. Alkyl halides turn out to be carcinogenic. Okay? But you do have this molecule called SAM, S-adenosylmethionine. This is biology's way of making iodomethane. Okay? Instead of CH3I, this is the equivalent of iodine for a biological system. Okay? Mother Nature overcomplicates things for good reason. Okay? And so you can simplify it as this. This is a good leaving group. It's S+. Okay? All this crap is a good leaving group. Okay? And so nucleophiles will attack here. This leaves, and you can get nucleophilic reactions to occur. So a nucleophile will react with SAM, and it will methylate the nucleophile. Okay? It's a methylating agent that is biocompatible, basically. This is very, very important for everybody in this room. This is how your fight or flight response works. Okay? You do not want to be in a constant state of fear and fight or flight. You'll die really quick, right? And so having the molecule adrenaline floating around in your bloodstream all the time will kill you. But generating it on demand when you have that need that fight or flight response, it's nice that you can synthesize it. And guess what? You synthesize it biochemically through an SN2 reaction. Noradrenaline, or norepinephrine, is not the active component. It's the nucleophile. You've got the nitrogen nucleophile right there. And we know that nitrogen's a better nucleophile than all those oxygens, right? It will react with SAM to methylate that nitrogen, and now you have adrenaline, which gives you the fight or flight response. It's generated on demand. You synthesize it. You do organic chemistry. When your heart starts to beat really fast and you're afraid of something, that's what's happening, okay? What other molecule is adrenaline related to that we talked about in Chapter 5 from my favorite TV show? Methamphetamine. If you look at it, if you took this away and those two oxygens away, you have meth, okay? It's very similar. They interact with very similar receptors. Okay, that's why people who are on meth are, right? They're in a constant state of fight or flight, if you will, okay? The take-home message here is that even though many of you want to go to medical school, what you're learning here is important. You will talk about these types of things, and if you don't have a basic understanding of the organic chemistry behind it, you will make errors in your understanding of the molecular biology, okay? Very important that you have an understanding of the organic chemistry. So I want you all to leave today knowing that this is important. We're not just running you through the torture chamber, okay? There is a purpose to this. All right, so tonight I will bring inverted 4. I forgot I didn't enter the grades in yet, but I'll bring your inverted 4 tonight at 6. We're going to meet downstairs in Tech 102 if you can come. I'm ordering some pizzas, so I need to know what do people want to avoid. Do people like pepperoni and sausage and...
I can't eat cheese.
You can't eat cheese? Oh, man.
So bring your own.
Yeah, bring your own food.
I'll bring my own.
I have rabbits up there. I'm coming to ask questions. I know I messed up.
How many people plan to be there? I need to kind of get an idea of... Okay. Several pizzas.